Okay guys, so let's get straight to the business. We are supposed to evaluate the Dirichlet? I hope it's Dirichlet, so whatever. Integral from 0 to infinity of sine of x over x with respect to x. How the hell are we supposed to do it? Because, well, this is not gonna follow from any basic properties of integrals and, you know, all of those basic stuff that we learn in the calculus 1 or 2, anything, yeah? We will have to use some tricky techniques here, and the most tricky technique is the famous technique. So yeah, this is exactly what I would like to do here. Well, the famous technique is basically just about plugging in some kind of a parameter into our integral, such that after taking the derivative of that integral with respect to that parameter, we will cancel out the most inconvenient variables, instances of our variables, such as this 1 over x here. Maybe I should have rather just mark it right there. Yeah, so this is the most inconvenient variable we have here in this integral. So what is some kind of a parameterized expression that we could plug into this integral in order to get rid of it? Well, I would honestly like to rewrite the integral as the integral from 0 to infinity of, and I would like to plug myself an exponential, let's say e to the negative some kind of a y multiplied by x, and then I would like to write my sine of x all over x dx, sine of x over x dx. And well, as you can see now, if I were to take the derivative of this entire thing with respect to that y, this parameter that I just introduced, then what I would get is just, I believe it would be negative x e to the negative y x, and so those x's would cancel each other out, and I would be just left with an exponential times a trigonometric function. That would be, well, just was awesome, but well, how do we go about it? I would like to introduce a new function, and I would like to call this function f of y. Yeah, so it's going to be my function with respect to that parameter. I mean, parameter is the variable with respect to this function, but the parameter with respect to this integral, you know, all of that weird stuff, yeah. So, well, what do we do now? Well, as I've just said, we would like to differentiate it. Yeah? So we'd like to calculate the derivative of f, which is the f prime of y. Well, this thing is just going to be equal to the derivative with respect to y of, of this integral, yeah, now it's better, of this integral of e to the negative yx sine of x over x dx. So I can just kind of take this d over dy here and just slip it under the integral sign, just take the partial derivative, but as my partial derivative sign looks awfully, I'm just gonna skip this part and go and calculate this this derivative straightforwardly. So what we're gonna get is the integral from 0 to infinity, doesn't change here, nothing changes here, of, that's gonna be negative e to the, maybe I will write it like this, negative x e to the negative y x sine of x all over x dx. As you can see, well, those x's nicely cancel each other out, and so what we are left with as the derivative of our f of y is just the negative e to the negative yx sine of x dx. And so you see, the nice thing is that, well, we just got rid of that 1 over x from the integral here. Now we are absolutely able to integrate this thing. And well, why does it solve our problem in the first place? I mean, why does it solve our problem at all? You see, if we are able to calculate this integral right there, which is just gonna be, well, evaluating this thing and then, integrating it with respect to y, which is gonna be far more convenient than doing this thing, this original integral, yeah, especially using the, calculus, calc 1 or calc 2 tools, stuff like this. Well, and then we just plug in the value of y being equal to 0, well, it would basically just give us the same result as plugging the value of y equal to 0 here, which would just result in, well, the original integral. Just, you know, go on and plug yourself a y equal to 0 here and here. You're gonna get just 1 times the sine of x over x dx. Something's gonna change, yeah? So let's go on and do it. We would like to now evaluate this integral. How can we do this thing? Well, this is gonna be just the regular integration by parts stuff that we see in calculus, and I really hope I don't get confused with all those negative signs, but we'll see about that. So we see an exponential and a trigonometric function. And so we probably are gonna have to just, you know, integrate it twice and then get what we started with, and then just do, you know, some kind of algebraic manipulation with that integral we got. Yeah, awesome. So integrating this guy by parts, I would like to rewrite it. So it's gonna be the integral from 0 to infinity of, well, negative exponential to the negative y x multiplied by the sine of x dx. I would like to, let's say, set this exponential to my u, and this sine of x is tweaked to my dv. I know that my v looks like my u, but, well, I really hope that this helps you distinguish between those two anyway. So we can now say it's gonna be all equal to, well, the antiderivative of the sine of x is just the negative cosine of x. Those two negative signs are gonna cancel each other out, so we're gonna be left with negative, so not negative but just positive e to the negative y to the yx, and then cosine of x in bounds of 0 and infinity, and then minus the integral from 0 to infinity. Now the negative terms in the exponential when taking the derivative of it are going to cancel each other out, and then the antiderivative of the sine of x is just the negative cosine, so the negative sign is going to cancel out with this negative sign over there. So we will actually be adding this integral from 0 to infinity, and then we will be given, well, differentiating this exponential, that's going to be y e to the negative yx, I mean, with respect to x, definitely. So yeah, that's gonna be y e to the negative yx, and then cosine of x dx. Well, just plug this exponential here, is gonna go to 0, plug this 0 here, is gonna go to, okay, so this entire thing is just gonna be nicely going to negative 1, and so we can rewrite this guy as negative 1 plus the integral from 0 to infinity of y times e to the negative yx cosine of x dx. But now, well, we just have to, you know, use the integration by parts twice here in this problem. Well, that's just because we are working towards achieving, well, the same integral we were trying to calculate from the very beginning, but, you know, at the very end, so then we can do some manipulations, you know, just double integrating by parts. So, well, now I would like to once again set this y times exponential to my u, and this cosine to my dv, lovely. And so what I'm gonna get is negative 1 and then plus, well, that's just gonna be y e to the negative yx multiplied by the sine of x in the bounds of 0 and infinity, and then, well, actually, once again, plus the integral from 0 to infinity of y squared e to the yx. Those negatives are gonna cancel each other out, and then multiplied by the sine of x dx. Well, the nice thing is that the guy we've got right here is the same guy as we have right there, with the small difference is that this guy here is just multiplied by a negative y squared, but it's not a problem at all. And also, this entire expression of this y e to the yx sine of x is just gonna nicely go to 0. I mean, you know, when x is infinity, then y e to the negative yx is just going to 0. And then when sine of x is given a 0, it also becomes a 0, so everything is lovely. Yeah, awesome. So we can just nicely go on and take this guy here to the left-hand side of this equation, or I guess it's, you know, like quadruple equation, but whatever. So we will get that the integral from 0 to infinity, or maybe I will just nicely write it as the f prime of y, because, well, this is exactly what that integral was actually equal to. minus y squared, or actually it's going to be plus y squared. Yeah, plus y squared f prime of y is equal to a negative 1. Yeah, so the only thing that was left over here. And so by this, we pretty nicely get that our f prime of y is equal to negative 1 all over 1 plus y squared. Well, that's pretty lovely because we know what the antiderivative of negative 1 over 1 plus y squared is. I mean, probably we should remember it from calc, yeah, I think from calc 1 even, not from calc 2, but calc 1. Whatever, you do the implicit differentiation and you get that is just the arctangent of x. And so the f of y is actually equal to the negative arctangent of y plus some kind of a constant. Well, that's awesome. Why is it awesome? We got a second representation for what our f of y is. Remember that we also set f of y equal to that integral, that class of integrals we wanted to evaluate from the very beginning. So, well, that's pretty awesome. Well, now what we can do is, well, kind of notice that we have no idea what the c is, and it might be nice to calculate it. So, well, how do we do this? Well, now just recall the first definition that we gave for f of y, which was the integral from 0 to infinity of e to the negative yx times the sine x over x dx. And well, since those two are equal to each other, we can just pretty nicely set them equal to each other. I mean, they're already equal to each other, and just take the limits. As well, let's say, yeah, y is gonna approach infinity. Yeah, so I would like to take myself the limits. The limit as y is approaching infinity of f of y is the same thing as the limit as y is approaching infinity of f of y. And so, well, as f of y are both equal to both this arctangent and this integral, we can say that the limit as y approaches infinity of this negative arctangent of y plus a c is nicely equal to the limit as y is approaching infinity, or y approaches infinity rather, of the integral from 0 to infinity of e to the negative yx sine of x over x dx. Okay, so, well, now the arctangents got an asymptote and a horizontal asymptote at pi over 2y equal to pi over 2. And so this entire thing is just gonna go and approach that pi over 2 as y is getting larger and larger. And so, well, that's pretty nice. That's pretty nicely. This y, as is going to infinity, this e to the negative y is actually gonna be going to 0. And also, it's pretty lovely because, you know, the sine of x over x is also going to 0. As x is getting larger, not larger. I mean, sine of x just oscillating, and x is getting, 1 over x is getting smaller. So this entire thing is here going to 0. And so we get that pi over 2 plus our constant, minus pi over 2, because it was a negative arctangent, plus c is going to be equal to 0. And so our constant we're looking for is going to be equal to a half of pi. Well, that's absolutely awesome, because now we got our almost the final answer. Yes, so we've got that our f of y is equal to the negative arctangent of y plus pi over 2. And now, well, for the last time, just recall what f of y actually was. F of y, by our definition, was the integral we wanted to calculate. However, now if we were to plug in once again y being equal to 0, then f of 0 would be equal to just the integral from 0 to infinity of e to the, well, 0, which is just a 1, so just the sine x over x dx, which is exactly the integral we wanted to evaluate in the first place. And so we see that as, maybe I write it here, that as f of y is equal to that negative arctangent of y plus pi over 2, we just go on and plug y being equal to 0 here and just get the value of our integral. And so doing that, we will nicely achieve that f of 0, which is our integral, which is our integral, is equal to negative arctangent of 0. Well, what's the arctangent of 0? That's just a 0, pretty nice. So you can check it, I don't know, and some graphical calculator. So that's just gonna be 0 plus pi over 2, which is pi over 2. And so we finally get our result, which is that the integral from 0 to infinity of sine of x over x dx is equal to pi over 2. That's exactly what we wanted to evaluate, to find, to prove, no, to find. So once again, what did we do in this problem? Well, we wanted to evaluate this awful looking integral of sine of x over x. So what we did is we introduced a parameterized expression that we just kind of slipped into our integral, and then, well, called our integral with that parameterized expression as some kind of a function in terms of the parameter in that parameterized expression. And then we took the derivative of that entire integral with respect to that parameter in order to get rid of this inconvenient x there, yes, so we got rid of it here. And then what we did is we evaluated the simple looking integral that we got after taking the derivative of that parameterized expression by parts, getting that actually we are able to get another representation for our original function of y, of the parameter, which is the negative arctangent of y plus some kind of a c. Then what we did is we just, well, kind of checked the limits as y is approaching infinity of both of our definitions for the f of y. And, well, we got that our constant is just a pi over 2, and then what we did is we just plugged a 0 into both of our instances of that f of y, getting that our original integral is equal to the arctangent, negative arctangent of 0 plus pi over 2, which is just the pi over 2, which is also our final result. And, well, that will be all. So I hope you guys enjoyed this video. Well, if you did, then like it and subscribe to my channel, so you won't miss out on any new videos I'm going to be posting out in the future. And actually I post every single day, or sometimes even 8-9 times a week, so there's a lot of stuff to miss out on. Lovely. See you next video. Bye.